5.1 Polynomial Functions. Alright, a polynomial function in one variable is a function of the form. So all this is saying that, sorry, you're going to hear my dogs bark. All this is saying that weird notation of like, what the heck is going on? All that means is standard form, highest exponent to lowest exponent. That's all that means. So remember, A's, those are called your constants, or the number just itself, no variable, that's called your constant. The number in front of the variable is called your coefficient. Coefficients, your exponents always need to be positive. So because this is a polynomial function, we need to make sure that when we have exponents that they're positive, because if they're not positive, they turn into fractions, remember? And of course, x is a variable. A can never be 0 for our leading coefficient. N is the degree of the polynomial, and the degree of the domain of a polynomial function is all real numbers. So every single polynomial function, the domain is all real numbers. So let's determine which of the following are polynomial functions. For those that are, state the degree. For those that are not, state why not. Write each polynomial function in standard form, and then identify leading term and constant term. Alright, our first one, it is a polynomial. Why? There's no radical. We do have a fraction, but the denominator is not in the bottom. If you can't really remember, let me remind you. So it's a polynomial if you have no fractions with a variable in the denominator. It's also a polynomial if there's no radical. Radical is this little thing. So if we look at this, we do have a fraction, but the variable is on the side. So this is a polynomial. It already is in standard form because it's highest exponent to lowest exponent. It goes 3, 2, then nothing. Now we can go ahead and figure out the degree. So the degree of the polynomial is the highest exponent, which is 3. Your leading term is the term attached to that exponent, so 4x cubed. Our constant is, if you have it, the number or a number without a variable, and we do have one. We have a number without a variable. It's -7. Awesome. Alright, next. It is a polynomial. There's no fractions. There are no radicals, so yes, it is. It's not in standard form, though, because it needs to be highest exponent to lowest exponent. So let's put it into standard form to -5x to the 4th plus x plus 3. Now we can go ahead and figure out our degree, our leading term, and our constant. So our degree is always the highest exponent, which is 4. Our leading term is attached with that exponent, -5x to the 4th, and our constant is just the number with no variable, which is +3. Alright, this is not a polynomial. It's not. Now, we're probably like, oh, I know why, because of the square root, or it's a cube root here. You would say radical. Okay, so on the surface, that is why. But remember how we were talking up here, how the exponent, that's what this is saying, that the exponent needs to be greater than 0. And it also has to be a whole number. It can't be a fraction. Now, why are you saying fraction? Where are you getting this from? So remember when we were doing in chapter 6 the square roots? So the cube root of x is the same thing as x to the power of 1/3. That's actually what we have. So the real reason is no, and it's why? It's because x is raised to the power of 1/3. And that's our answer. So if you have an if you have a radical, switch it to an exponent fraction, and that is why it's not a polynomial. All right, next one. We have a fraction, but more importantly, we have a variable in the denominator, so this is not, it's not a polynomial. So on the surface, we know why. It's because there's a fraction with variable in the bottom, which is denominator. Now, again, that's not the real reason why. So I'm going to bring that variable in the denominator out. If we bring it out by itself, it's 1 over x to the fourth. Remember, that's x to the negative fourth. That is not a polynomial, because polynomial needs to be a whole number and needs to be greater than 0. So the real reason is no, because x is raised to the power of 1/4. Sorry, negative 4. All right. So, is this a polynomial? Absolutely it is. Why? There are no fractions whatsoever, and there's no radical. Doesn't matter what it looks like. As long as those two things are not there, it is a polynomial. So first off, we need to get this into standard form. So we need to FOIL everything. So we have negative x cubed, and then x minus 3, x minus 3. Let's go ahead and FOIL. And when we do, we get negative x cubed times x squared minus 6x plus 9. We're going to distribute. So we get a of x equals negative x to the fifth plus 6x to the fourth minus 9x cubed. So yes, it is a polynomial, and now we have it in standard form. That's a horrible 5. Let me rewrite that. All right. See this 5 right here? Let me change that color. See that 5 right there? There is something special about that 5. Well, yes, that's the degree of the polynomial, but you know you don't have to FOIL to find the degree of the polynomial, because what's 3 plus 2? 5. All right, that's our degree. It's 5. Now remember, our degree is always attached to the leading term, so our leading term is negative x to the fifth. And then we need to find our constant. You're like, there isn't one. We don't have something there. We don't have just a number without a variable. We don't. You're right, we don't. But how do we say no, we don't in math? We say 0. There's always a 0 there, so our constant is 0. Just like how there's always a 1 under every number, there's always like 4 over 1, 3 over 1. There's always a 0 at the end of everything. So if you don't have a constant, we say 0. Alright, last one. This is a polynomial. Why? There's no radical, there's no fraction. So this is a polynomial. It is in standard form, because how can you, I can't rearrange it. We're good to go. So our leading term is 9. That's the only thing we have. Our constant is 9, because that's the only thing we have. We can find the degree here. We can. The degree is always attached to exponents. So I'm going to make this have an exponent, and I can, because we can do 9 times x to the power of 0. The reason why we can do that, because what's anything to the power of 0? It's 1. So 9 times 1 is 9. You see how I didn't change the values? It's the same number. So our degree is 0. So if you don't have a variable, your degree is 0. Because again, how do we say we don't have something in math? We say 0. Alright, this little box right here, this yellow box with the blue, that is for my people going to calculus. Just, you should always save your notes, especially if you're going on to other math classes, because a lot of the times you're like, oh, okay, I can't really remember how to find domain of a fraction, but you know, my college algebra notes has that. So it's always good to go back and look up things that you might have forgotten, because you know, it's use it or lose it. So this is what that chart is. It talks about like what kind of functions we have and what shapes do they make. Okay, I'm not going to go over that box, but it's for those of you that are going on to calculus. You should. All right. When speaking of calculus, when you get to calculus, if you do, you're going to learn how to graph every single type of polynomial function there is. So polynomial functions, they're smooth and continuous. By smooth, we mean that the graph contains no sharp corners or cusps. By continuous, we mean that the graph has no gaps or holes and can be drawn without lifting your pencil from the paper. So the difference is smooth. You see the left one, part A? You see how that's nice and smooth? It flows. But B, that doesn't flow. It has a crazy corner and a cusp, and it has a hole and it has gaps. That's not smooth. Real zeros. Real zeros, this is where I call upon you of, do you remember what they are? I have given you 3 names for something. Real zeros are the same thing as x-intercepts and roots. So if f is a function and r is a real number for which f of r equals 0, then r is called a real zero of f. So all that is saying f of r equals 0, that's saying f of x equals 0, which just means y equals 0, and we know that just means the x-intercept. As a consequence of this definition, the following statements are equivalent, so meaning because we know this, we can guarantee this bit of information. R is a real zero of the polynomial function f, R is an x-intercept of the graph of f, x minus r is a factor of f, r is the real solution to the equation f of x equals 0. So remember, real zeros, all we're talking about is x-intercepts. That's it. This whole r thing, where it's saying we have r, all that means is x equals a number. But instead of x, they're saying r equals a number. That's all. So we're just saying that this is an x-intercept. That's all. And then the x minus r is a factor of f. All that is saying is, you know how when you factor, you get x minus a number equals 0? That's all that's saying. And then here, all that's saying is y equals 0. That's all. I'll put that over here. I don't know why I put that over there. There we go. So if I gave you like a quick example of what all this meant and kind of like refer it back to what we know. So say we factored, and say we factored and we got this. So wouldn't we do x minus 4 equals 0, add 4 over, so we get x equals 4? That's all, literally, that is all that is saying. But now we can go either top to bottom or bottom to top. Because if we're given the x-intercept, I can find where that equation actually came from. Cool, right? Identify the real zero of a polynomial function and their multiplicity. So before we actually get to anything, let's talk about the word multiplicity. So multiplicity, that actually means how often something repeats. So that something in math is how often a term repeats. So if I gave you an example of that, like I said, if we had like x plus 3 squared, that's the same thing as x plus 3, x plus 3. So you see how it repeats 2 times? So that means it would have a multiplicity of 2. Alright. If a polynomial function f is factored completely, it is easy to locate the x-intercepts of the graph by solving the equation f of x equals 0, meaning we just make y equals 0. It's called the zero product property. So you know every time we're like, set the equation to 0, set the equation to 0, especially when we were solving quadratics, that's actually called the zero product property. When we graph a polynomial, this is something that it will look like. It's going to be smooth, it's continuous, it crosses x-axis, it touches the x-axis, and so on. All right, we will start to graph in the next section. Finding a polynomial function from its real zeros. So now we are given the x-intercepts. We're given the zeros. We can find the exact polynomial that came from. So cool. All right, so we have our zeros. So our first zero is -2 with a multiplicity of 2. Our next zero is just 0 with no multiplicity. You see the little semicolon? See the semicolon? That's what's separating each zero. So see how we have the next semicolon? So we have a new 0. Our next 0 is at 5. And it has a multiplicity of 2. The degree is just telling you at the end, your final answer should have a degree of 5. That's all that's saying. All right, because it says to find a polynomial function, we know it's going to be coming from x minus r. X minus r, the r, those are your zeros. So this is an r, that's an r, that's an r. So we're just going to plug them in to each of them. All right, so we have x minus our first 0 of -2. We'll talk about multiplicity in a second. We have our next one of x minus r, which is 0. And then we have x minus r, which is 5. So the multiplicity is the little exponent that goes on top. So see our first one has a multiplicity of 2, so it goes here. The middle one has no multiplicity, and our last one has a multiplicity of 2. And because it says polynomial function, we know it's going to be f of x. Now from here, we just simplify. That is it. So forever, how many zeros you have, that's how many times you have to do x minus r. So you see we have 3 zeros. That means we had to do x minus r 3 times. Let's clean this up. So we can clean this up into plus 2 squared, x, and x minus 5 squared. So we have to FOIL. That means we have x plus 2 times x minus 5, x minus 5. We FOIL our first one, so we get x squared. Make that smaller. We get x squared plus 4x plus 4. Still have that x in the middle. And then we FOIL our next one to get x squared minus 10x plus 25. We can go ahead and just distribute the x. I feel like that's going to be the easiest thing to do right now. And when we do, we get x cubed plus 4x squared plus 4x all times x squared minus 10x plus 25. All right, I don't know about you. I cannot FOIL well when it's trinomial. When you start busting out trinomials, it's hard for me to FOIL for some reason. I just can't see everything that's there. I always mess up. So I just thought of a way to do it back in the 8th grade of just use a multiplication chart, because that's all you're doing. You're just multiplying. So for our first one, we have 3 terms. So we have x cubed, make that smaller, x cubed plus 4x squared plus 4x. Our next one, we have 3 terms again. We have, x squared negative 10x, and positive 25. So I write them vertically and horizontally for ever how many terms they have. And now we're going to multiply. So you do x squared times x cubed is x to the 5th. X squared times 4x squared is 4x to the 4th. X squared times 4x is 4x cubed. Negative 10x and x cubed is negative 10x to the 4th. Negative 10x times 4x squared is negative 40x cubed. Negative 10x times 4x is negative 10x squared. 40, my bad. Negative 40x squared. 10 times 4 is 40. 25 times x cubed is 25x cubed. 25 times 4x squared is 100x squared. And then 25 times 4x is 100x. And why I like to do this is because it's nice and neat. You can see everything there is. You won't miss anything. You won't miss to factor, or you won't miss to multiply anything. But there's another reason why I do this. All right, now we have to combine like terms. So diagonally are where your terms are going to go together. So here, you see how there's nothing diagonal of it in the white part? So that means our first term will have x to the 5th. Then if we keep going, you see how these are diagonal of each other? That means we combine these terms. Also, they have the same exponent. That's why we combine them. So we get negative 6x to the 4th. Keep going on. We combine all these because they're all x cubed and they're all diagonal from each other. So 25x cubed minus 40x cubed plus 4x cubed, we get negative 11x cubed. Alright, next we do our x squareds. So 100x squared minus 40x squared is 60x squared. And you see how there is nothing, I'm running out of colors here. We'll just do this. There's nothing with 100. There's no diagonal, so we just write it as 100x. That is our polynomial function. Cool, right? Alrighty. More about multiplicity. So numerically, we don't really pay attention to numerically in this class. We only talk about graphing. So if R is a zero of multiplicity, so let's just talk about graphing. So for graphing, the graph of f touches the x-axis at R, meaning if we have a zero of even multiplicity, so if we had like x minus 3 squared, so you see how it repeats 2 times? So that's even multiplicity. That means at 3, 0, it touches the x-axis. Because that's where the x-intercept would be, right? Because you would do x minus 3 equals 0. So it'd be x equals 3. And then here, if we have an odd multiplicity, say we had like x plus 4 to the 7th. So you see how that's an odd multiplicity? It's an odd exponent. So that means at negative 4, 0, it crosses the x-axis. You'll see what we mean when we actually start to graph this in the next section. How do I remember this? There's actually a neat trick that I came up with. So see how it's even and it touches? E.T. Remember in E.T. where he touches? That's how I remember that. If you haven't seen E.T., watch it. It scares me still, but it's a really good movie. So, how do you remember that? Even touches, E.T. E.T. touches, okay? Also, how do I remember O.C.? Odd crosses? I remember that by O.C. because coincidentally, right now, most of us live in Orange County. When I was growing up, I lived close to Orange County, so it was easy for me to remember. So I remember ET, even touches, OC, odd crosses. We're going to talk way more about that when we start to graph. Right now, we're just learning how to find multiplicity, okay? All right, so identify real zeros and their multiplicity. This is factored. How do I know it's factored? Because everything it's parentheses and it looks factored, right? It looks like you already factored it. In this class, we don't have to factor crazy stuff. We're already going to give it to you factored. So we have 3 terms. We have 6x cubed. We have x minus 5. And we have x plus 1/4. So we have 3 terms. We can find the real zeros. We can find the intercepts, because what we can do is pretend the exponents aren't there. We can do 6x equals 0, so x equals 0. We can do x minus 5 equals 0, so x equals 5. And then pretend the exponent's not there. When you're finding the real zero, you don't care about the exponent, because that's just how many times it repeats. So here we have x plus 1/4 equals 0, so x equals negative 1/4. Now we start to care about multiplicity. So for this one, we have cubed. So that means 0 has a multiplicity of 3. It repeats 3 times. So since it's odd multiplicity, we can say that the graph odd, it crosses. So the graph crosses at 0, 0. Because remember, when you find the x-intercept, y equals 0. So that's why it's 0. Alright, so here at x minus 5, there is no exponent. But remember, if there isn't something, there's usually something there that's hidden away. And there is. There is a 1 there. There's always a 1. So this actually has a multiplicity of 1. So since it's multiplicity of 1, it crosses, because that's odd, so we could say it crosses at 5, 0. Alright, last but not least, we have our next multiplicity. Sorry, I wanted to circle that in proper color. Let's do pink. Alright, so here, x plus 1/4, it has a multiplicity of 4. Since it has a multiplicity of 4, that's an even number. That means it touches at negative 1/4, 0. Alright. And again, when we start to graph, you'll see why that's so important to know. It's going to give us the shape of the graph. Alright, turning points. If f is a polynomial function of degree n, meaning that you have a polynomial and it has a degree, then the graph of f has at most n minus 1 turning points. So that's degree minus 1. It gives you turning points. If given turning points, the degree of the polynomial can be found by adding 1 to the number of turning points on the graph. And that's what we have in these pictures below. We're given how many times it turns. So since we know how many times it turns, we can find the least degree. So which graph in the figure could be the graph of a polynomial function? For those that could be, list the real zero and state the least degree the polynomial can have. For those that are not, say why not. Alright, our first one. No, not a polynomial. No. Why? There's a gap and there's a hole. Cool. Alright, our next one to the right. Is that a polynomial? Yeah, it's smooth, it's continuous, it has a flow. So yes. Since it is, let's go ahead and list our zeros. So our zeros are the points where they cross the x-axis or touch it. So our first one here, we have negative 3. Our next one, we have negative 1. And then our last one, we have positive 1. Since it's asking what are the zeros, it just wants the number, not the point. Alright, let's go ahead and find the degree. So to determine the degree, we need to know how many times it turns. They're called turning points. So it turns 1 time, 2 times. So to find the degree, you do turning points plus 1. So 2 plus 1, we get 3. That means the degree, the least degree of this polynomial is 3. That means that little exponent at the beginning, it's going to be 3. Alright, is this a polynomial? No, it is not. Why? Right there. That's a sharp turn, or also known as a cusp. That's the only reason why. It's not smooth. That's not smooth. That's harsh, right? It's really, really jagged. So no, I would say sharp turn. Okay. The last one, is that a polynomial? Absolutely. It's smooth, it's continuous, it has a flow. So yes, since it is, let's go ahead and figure out the zeros. We have one at -3, and then we have another one at 0. Now that we have our zeros, they're called zeros because you make the equation equal to 0. That's why they're called zeros. Let's find our degree. To find our degree, we need to figure out how many turning points we have. So it turns once, twice, 3 times. So to find the degree, we do turning points plus 1. So 3 plus 1, it's 4. So that means our degree is 4. End behavior of the graph of a polynomial function. So sometimes when you graph polynomials, you really won't have a lot of information for it, so it's kind of hard to figure out how does it end? Like where do the arrows go? You know what I mean? So the end behavior of the graph of the polynomial function is the same as the graph of the power function, meaning that all it means is your end behavior resembles your leading term. So this is what a polynomial could look like. The middle is what's going to be different, but the ends, the arrows, are what's going to match up. Alright, so some key information here. Whenever we have a polynomial function, if we have an even, so say we had like x squared, x to the 4th, x to the 6th, stuff like that, we're going to have double arrows. The next one is just the opposite. If we had like negative, because it just all it means is just negative. So if we had like negative x squared, negative x to the 4th, negative x to the 6th. Okay, it goes down because it's negative. The next one, it's if we had odd exponents. So if we had like x cubed, x to the 5th, x to the 7th. And next would just be the negative versions of that. So if we had like negative x cubed, negative x to the 5th, negative x to the 7th. So the middle is what's going to be different, but what's going to be the same are the ends. That's why it's called end behavior. We know what it's going to look like. We know what it's going to do when we get to the ends. Alright, so we're going to identify the graph of a polynomial function. Which graph in the figures could be the graph of x to the 5th plus ax cubed plus bx squared minus 2x plus 3, where a and b are positive. So meaning, we don't really have a polynomial, but with what we're given, can we figure out what it might look like? Oh, absolutely. So the first thing we want to do is identify the degree. So the degree of the polynomial is 5. So what that tells me is that it turns 4 times. I can't spell today. It turns 4 times. How do I know that? Because 5 minus 1 equals 4. So let's look at our graphs and figure out which ones turn 4 times. Does A turn 4? 1, 2, 3, 4. It does. B, 1, 2, 3, 4. It does. C. Oh, C turns a bunch. That's definitely not C because it turns 1, 2, 3, 4, 5, 6, 7, 8 times. Nope. And D, 1, 2, 3, 4. Yep. So the only thing we were able to get rid of was C because it didn't turn 4 times. Awesome. Now we can go ahead and take some more information from here. We can figure out our y-intercept. Our y-intercept is always the number at the end. It's always your constant. So here our constant is 3. So that means our y-intercept is 0, 3. Let's look for this graph that could kind of represent 0, positive 3. That's not positive, so it can't be A. That could be 0, 3. D could also be 0, 3. So now we're narrowing it down to B and D. What's going to tell us the last bit of information we need is our leading term. So our leading term is x to the 5th. That means we can figure out the end behavior. So this is an odd exponent. Since it's an odd exponent and it's positive, so it's positive x to the 5th, it resembles end behavior of C. We know that. So since it resembles, C in the end behavior, we know the ends are going to be like this. Whatever's in the middle was whatever in the middle. We don't care. We just care about what the ends look like. So let's try to match up our ends. They have to go down, then up. This goes down, then up. D does not go down, then up. So it is not D. Our answer is B. So to determine if it's a graph that matches the function, you figure out the degree, the y-intercept, and your leading term, which gives you your end behavior. All right, last example. Yeah, this is a lengthy section. Before we got the new book, this used to be like 10 examples. It took 2 classes. It was pretty crazy. All right, finding a polynomial function from a graph. Find a polynomial function whose graph is given. Use the smallest degree possible. So we're given a graph. Now we're actually going to figure out the function that represents this graph. So looking at a graph, can we figure out the polynomial function that is this graph? We absolutely can. The first thing we want to do is figure out our zeros. So we have 3 of them. We have a 0 at -1. We have another one at +1. And then we have another one at +2. What's going on here? There we go. Okay. Nope, my bad. I guess not. Okay, there we go. Alright, so we have our zeros. Since it's asking for a polynomial function, we know we can use x minus r. So let's go ahead and plug these each into x minus r. So we have x minus -1. Because remember, these actually represent r, because these are our zeros. And then we have, wrong color, x minus 1. And then last but not least, we have x minus 2. So we can clean this up. We have x plus 1, x minus 1, and x minus 2. So now we need the little exponents. Let's look at each of these. So at -1, 0, right here for our green one, it touches. Since it touches, we know that it has to be even. So that means that this has to be an even exponent. So it has to be x plus 1 squared. Because it says to use the smallest degree possible, that's why we use squared. Alright, next we go to our blue one, our positive one, which turned into negative. So our x at +1 it crosses. So it crosses at 1, 0. That means it has to be odd. So odd, it crosses. That means our exponent has to be 1. So we have x minus 1 to the power of 1. All right, last, our next one, our orange one, our x-intercept at 2, our 0 at 2. So that means since it crosses at that intercept, that means it has to be odd. So we're going to have x minus 2 to the power of 1. Now that we have our exponents and we have our factors, we can go ahead and just put them into f of x equals. Now, we go back. This is the part that might trick us up. Do we have our a, our growth factor? We don't. We're just given zeros here. So because we're just given zeros, we need to figure out what a is. Okay. Now we plug everything else in. We'll have x plus 1 squared, x minus 1 to the first, and x minus 2 to the first. So to figure out a, to find a, we use the y-intercept. The y-intercept is 0, 4. So that means x is 0 and y is 4. We're going to plug it in. So we have 4 equals a times x, which is 0, plus 1. Just going to fill these in. So we just replace all of our zeros with x's and simplify. So we have 4 equals a to the power times 1 squared times negative 1 to 1 and times negative 2 to the 1. So meaning we have 4, so 1 squared times negative 1 times negative 2 is just positive 2. Positive 2a, because negative and negative become positive. And then divide by 2, so we get 2 equals a. So our final answer, we literally just plug it back in. We have f of x equals a, which is 2 times x plus 1 squared times x minus 1 times x minus 2. You don't need to FOIL for that homework or the test. That's how it's exactly going to be.